Hello friends, in this video let us take an example and draw the reactance diagram for this single line transmission, single line diagram by using the per unit system representations. So I am having a generator, a transformer T1 and a transmission line of 64 km and transformer T2 and two motors M1 and M2. So the ratings are given here: 300 MVA, 20 kV, 20% is sub-transient reactance, and 350 MVA, 230 upon 220 kV, 10% reactance. And for the transmission line, it is of 64 km and the series reactance is of 0.5 ohm per kilometer. And here, this transformer T2 is composed of three single phase transformers, each having a rating of 127 upon 13.2 kV, 100 MVA and 10% reactance. And here 200 MVA, 100 MVA, 13.2 kV for both the motors and 20% reactance for both the motors. Now we are required to find the impedance diagram for this transmission line. So you are asked to take the base MVA of the generator and base kV for this generator circuit. So 300 MVA is the base for this whole transmission line, and for this generator circuit I am having 20 kV as a base. And before proceeding to the calculation, we have to divide this any transmission line into number of zones. So the number of zones depends on the kV, base kVs. So where you can form the base kV to which part. So here you will be having one zone. This is second zone because they are connected to the same points here. Here also they are connected to the same points, and this is your third zone. Now 20 kV is the base here, and you have to find what is the base in this transmission line. So I have been given the 230 upon 20 kV. So whenever you are given like ratio, this is your turns ratio. That is, turns ratio is generally from IEEE standards. The turns ratio is given by number of turns in HV winding to number of turns in LV winding. So this is your 230 upon 20 kV. So generally on the transmission generating side, I am having a step up transformer. That means here I am having 20 kV and here I am having 230 kV. Thereby it will be your step up transformer. Now if you take the voltage ratio is the voltage in the primary winding to the voltage to the secondary winding is your voltage ratio, whereas turns ratio is the number of turns in the HV winding to the number of turns in the LV winding. Now we have to find the base kV in the transmission line. So to find the base kV in the transmission line, I am having the base kV here will be equal to 20 kV into 230 kV upon 20 kV. So kV, this will be cancelled and my base kV will be 230 here. Here it is 20. And similarly, I want to find the base kV in this zone. So the base kV in this zone will be 230 into 13.2 upon. So the line to line voltage here will be given by under root of 3 into 127 upon 13.2. So this will be 220. And if I multiply the 3 phase power, it will be 3 into 100, so 300 MVA. As this is composed of 3 single phase transformers, this is phase voltage. And if I want to convert line to line voltage, I have to multiply with under root of 3. And this is one phase transformer, 100 MVA. So 3 transformers, that means 3 into 100 MVA. So here it will get 13.8 kV. So in this region I am having 13.8 kV as a base kV. Now I am required to find the per unit reactance of the generator, transformer T1 and the transmission line and the transformer T2 and these two motors. So if I write for generator G1, my X per unit nu from given by, or you can say we are neglecting the line to ground capacitance XC and the resistors. So by neglecting these, we are having only the inductance or the reactance of the the reactance of the inductive components only. So x per unit new will be given by x per unit old into MVA new upon MVA old into kV old whole square by kV old kV new whole square. So this is your x per unit new formula. Now all the given values in the question are the old values. So the new values are what we have found, the 20 kV, 230 kV and 13.8 kV are the new values, and the new MVA is the base MVA assumed for the whole transmission line. So this is a new MVA and the found kV is a new kV. So all the previous given values are the old values. Definitely remember this, what are the old values and what are the new values. So if I calculate for the generator, G1 x per unit old is a given value, that is 0.2 into MVA new is 300 upon 300 into 20 upon 20. So this will yield me 0.2 per unit. Now if I go for the transformer T1, I am having x per unit old is equal to 0.1 into MVA new is the 300 upon MVA old is the 350 into 20 upon 20. Because kV old is the 20, this side is 20 and new is also 20. So I will get this value as around 0.085. Now for the transmission line TL, I am having the new value is, I am given 0.5 ohm per kilometer, but it is of 64 kilometers. So 0.5 into 64 into the MVA new is 300 upon the base value is 230 square. So this gives me 0.182 per unit. Now for transformer T2, I am having the old value x per unit old is 0.1 into the MVA new is 300 upon MVA old is 3 into 100, 300 into, if I take this portion, this is 220 kVA, under root of 3 into 127 gives you 220 and here it is 13.2. So my kV old is 220 upon kV new is 230 whole square. So this gives me 0.091. Now similarly, if I calculate for the motor M1, it will be 0.2 into your new base MVA is 300 and you are having the old base MVA, that is 200 MVA for motor M1. So 200 into your old kV is this. You are having the kV old is, so 13.2 upon the new kV we found is 13.8. So 13.8 it is whole square. This gives you 0.274. Now similarly, if we calculate for the motor M2, I am having for M2 x per unit will be equal to 0.2 is a subtransient reactance. So 0.2 into new base MVA, that is 300 upon the base MVA given is 100 into 13.2 upon 13.8 whole square. So this gives me 0.549. So per unit. So these are the reactances, or you can say new reactances we have found on a common base value for the transmission line given. Now if you want to draw the reactance diagram, what we have to do is we have to replace the motor or the rotating machines with the EMF and their internal impedances, and the rest of the transformer and the transmission line can be represented by the reactances. Here we are neglecting the resistances and the capacitance that is between the line and ground. So we are left with only the inductance part. So let us represent. First we are having a generator. So generator will be represented by a EMF and with the internal impedance, and next we are having a transformer. This is our transformer. Next we are having a transmission line. This is a transmission line, and next again we are having a transformer, and here I am having a bus bar, and to that bus bar two motors are connected, and as these motors are also rotating machines, generally rotating machines are represented by a EMF source or voltage source with its series impedance. So this is E1, let us say E2, and these are connected like this. Now the polarity can be indicated like this. Now we know for the generator G1 we have found the reactance as 0.2 per unit, that is this can be written as J 0.2. For the transformer T1 it is J 0.085. As these are imaginary, I am writing here J, or you can say the reactive part, we are writing it as J, and for the transmission line the TL, the impedance is 0.182. So J 0.182 ohm, and for the transformer T2 I am having J 0.091 ohm. These are all the per unit values, and for motor M1 I am having J 0.274, and for the motor M2 J 0.549 reactances of the given transmission diagram. So whenever you are given some transmission line, what we have to do is we have to split it into zones. So the zones can be split on the basis of the kV that we have to calculate. So suppose if they are on the same point, then that will fall under one zone, and if they are at different point, they will fall in the next zone. So as these are the same potential, they will fall in a zone 1, and these are in the same potential, they will fall in the zone 2. As these are in the same potential, they will fall in the zone 3. So same potential can be divided into zones, and by thereby you can have to calculate the kVs, the new kVs, and from there you are having this formula x per unit new, that is x per unit old into MVA new by MVA old into kV old square by kV new whole square. So by putting the values, given values in this formula, you can get the reactances of new reactances of the transmission line given, and thereby you can draw the reactance diagram or the impedance diagram for your transmission line. Now here you have to cautious here, because the rating given here it is 230 by 20 kV. That means you do not have to assume that this is 230 or this is 20. But as we are on the generating side, we are always prefer to use step up transformers. So as this is 20 kV, generator kV is 20 kV, that means the 20 kV of the rating being given, or the ratio, turns ratio will be applied here 20 kV and 230 kV this side. So do not confuse with the turns ratio being given, because the turns ratio and the voltage turns ratio are different. According to IEEE standards, the turns ratio will be given by the number of turns in high voltage winding to the number of turns in low voltage winding, whereas your voltage turns ratio will be given by voltage in primary to voltage in secondary. So you have to remember this definitely. And for generating side we are using step up transformers, and for distribution side we are using step down transformers. Thereby you have to see the turns ratio given, and thereby you can calculate the kV easily without any confusion or committing serious errors. So I hope you understood how we solve this very simple problem. So please subscribe to the channel. Thank you.